Far above us, in the quiet dark between the stars, there is a kind of light that has been traveling since almost the very beginning of time. It reaches us tonight the same way it reaches us every night, faint and ancient, carrying with it a story about where we come from and where we sit within everything that exists. Tonight we are going to sit with that story for a while, slowly. The way you might sit by a window watching rainfall on a street, letting your mind wander through something old and strange and quietly beautiful. For roughly 400 years, modern science has rested its full weight on a single, humble assumption. It is called the Copernican principle, and it says something very simple. There is nothing special about where we are. We are not at the center of anything. Our sun is one ordinary star among hundreds of billions in our galaxy, and our galaxy itself is just one faint smudge of light among trillions of others scattered through an endless, uniform sea of space. For centuries, every new discovery seemed to confirm this idea a little more. Earth was not the center of the solar system. The sun was not the center of the galaxy. The galaxy was not the center of the universe. Each time astronomers looked more carefully, they found the same lesson repeating itself. We are ordinary. We are unremarkable. We are, in the kindest and most scientific sense of the word, nobody special. In physics, this idea has a more technical name. It is called isotropy, and it means that if you look far enough into the distance, in any direction at all, the universe should look statistically the same. There should be no favored direction, no cosmic up or down, no built-in left or right. This is not simply a philosophical preference held by tired, humble scientists. It is baked directly into the mathematics that describes the universe we live in. Our current model of cosmology, known as lambda cold dark matter, or lambda CDM for short, depends on this assumption to function. If the universe has a grain to it, a preferred direction sewn into its very fabric, then the equations we use to describe gravity, the expansion of space, and the aftermath of the Big Bang begin to strain and, in some cases, quietly fall apart, to test whether the universe really is smooth and directionless in this way. Scientists turn to the oldest light there is. It is called the cosmic microwave background, usually shortened to the CMB, and it is essentially a baby picture of the universe, taken when the cosmos was only about 380,000 years old. Before that moment, the universe was so hot and dense that light could not travel freely. Photons were trapped, constantly scattering off free electrons in a hot plasma, the way light scatters inside a thick fog. But as the universe expanded and cooled, electrons and protons finally combined into neutral hydrogen atoms, and space became transparent. Light was, for the first time, free to travel in straight lines. That light has been traveling ever since, stretched and cooled by the expansion of space. Until today, it arrives at our telescopes as faint microwaves, just a few degrees above absolute zero. When you look at a map of this ancient light, it appears as a chaotic speckled pattern of slightly warmer and slightly cooler patches, scattered across the whole sky. To most people, it would look like static on an old television screen. But to a cosmologist, that randomness is beautiful, because it is exactly what the theory predicts. It is proof that the early universe was a smooth, well-mixed soup of energy, with only tiny, random fluctuations seeded by quantum processes in the first fraction of a second after the Big Bang. Those fluctuations were the seeds that would later grow into galaxies, clusters, and the vast cosmic web we see today. But when scientists began to peel back the layers of that noise, separating the map into its different components, the way you might separate a chord of music into its individual notes, they found something that, according to everything we understand about physics, should not be there. This process is called multipole expansion. and it is one of the more elegant tools in a cosmologist's kit. Think of the cosmic microwave background as a complicated musical chord made up of many notes layered on top of each other. Multipole expansion is simply the mathematical technique for breaking that chord down into its individual notes, each one corresponding to a different scale of pattern across the sky. The lowest note, called the monopole, is just the average temperature of the whole sky, a single number with no pattern at all. The next note is the dipole, which reflects the fact that one side of the sky appears very slightly warmer than the other side. This happens because our solar system, along with the rest of our galaxy, is moving through space at a considerable speed relative to the cosmic microwave background itself, somewhere in the neighborhood of 370 kilometers per second. This motion creates a Doppler effect, warming the light in front of us and cooling the light behind us. And scientists subtract this effect out immediately, since it tells us about our own motion rather than about the early universe. After the dipole comes the quadrupole, which divides the sky into 4 broad patches of relatively warmer and cooler regions. After that comes the octupole, which divides the sky into 8 smaller patches. In a universe that began with a truly random period of cosmic inflation, these different notes, these different multipoles, should be completely independent of one another. There is no known mechanism in the standard model of cosmology that would cause the quadrupole and the octupole to line up or correlate with each other in any meaningful way. They are supposed to be the product of separate, random quantum fluctuations that occurred in the first trillionth of a second of the universe's existence. Expecting them to point in the same direction would be a little like expecting 2 people in separate rooms, each throwing a handful of dice, to somehow produce the exact same sequence of numbers purely by chance. In the year 2005, a group of researchers working with data from the Wilkinson Microwave Anisotropy Probe, usually called WMAP, decided to carefully measure the orientation of these 2 specific notes, the quadrupole and the octupole. What they found was a statistical oddity that no one had fully anticipated. The axis of the quadrupole and the axis of the octupole were almost perfectly aligned. Rather than pointing in random, unrelated directions, they were stacked on top of one another, both pointing toward the same patch of sky. The physicist Joe Amaduzio, along with his collaborators, gave this strange alignment a memorable and slightly ominous name. They called it the axis of evil, a playful but pointed reference to just how much trouble this pattern could cause for our standard models of cosmology. If it turned out to be real. If the largest structures visible in the early universe truly are aligned with one another in this way, it suggests that the universe is not isotropic after all. It suggests that space itself might have something like a preferred direction, a top and a bottom, in violation of the cosmological principle, which is the working assumption that the laws of physics and the overall distribution of matter and energy are the same everywhere and in every direction. The strangeness of the discovery did not stop there. When researchers projected this newly discovered axis onto a map of our own solar system, they found something even more unsettling. The axis sat almost exactly along the ecliptic, which is the plane traced out by Earth's orbit around the Sun. It seemed to respect the position of the equinoxes as well, the 2 points in the year when day and night are of roughly equal length. This created an enormous logical puzzle. The light of the cosmic microwave background was set in place nearly 14 billion years ago, when the universe first became transparent. Our solar system, by contrast, only formed around 4.5 billion years ago, an almost trivial span of time by comparison. There is, on the face of it, no obvious reason why a pattern etched into the fabric of the universe near the very beginning of time should somehow be aware of, or aligned with, the orbital path of a small, unremarkable planet circling a middle-aged star. itself just one of billions scattered through an ordinary spiral galaxy. When researchers calculated the odds of this kind of alignment happening purely by chance, the number came out to be less than 0.1%. That might sound, at first glance, like there is still plenty of room for a coincidence. But in the world of physics, a 99.9% level of confidence that something unusual is going on tends to mean one of two things. Either we have stumbled onto a genuinely new piece of physics, or there is a subtle, hidden error somewhere in our data or our methods, one that has managed to fool multiple generations of increasingly sophisticated instruments. When this result first appeared, the overwhelming reaction from the scientific community was not excitement. It was caution, and in many cases, outright skepticism. Extraordinary claims, especially ones that threaten a foundational assumption of modern cosmology, tend to be met first with an assumption of error. Many researchers suspected that the WMAP satellite might have some subtle bias built into its sensors, perhaps a slight asymmetry in how its detectors were calibrated. Others wondered whether the process of subtracting out the light from our own galaxy, a necessary but delicate step in producing a clean map of the cosmic microwave background, might be leaving behind a faint shadow that only looked like a genuine pattern. For years, the working assumption among many cosmologists was that the axis of evil would simply dissolve once better instruments became available. That better instrument eventually arrived in the form of the Planck satellite, a mission built by the European Space Agency and launched in 2009, where WMAP had been a pioneering but relatively modest instrument. Planck carried far more sensitive detectors, cooled to extraordinarily low temperatures, and designed to map the cosmic microwave background across a wider range of frequencies with much finer resolution. Planck was, in a very real sense, built to settle the question: if the axis of evil was simply an artifact of WMAP's limitations, a more precise instrument should make it vanish. When the first major batch of Planck data was released in 2013, and then refined further in 2015 and again in 2018, the results were not what many cosmologists had hoped for. The alignment between the quadrupole and the octupole remained. Planck confirmed the existence of the axis across multiple independent frequency channels, which made it considerably harder to argue that the pattern was simply a leftover shadow of poorly subtracted galactic dust. If the anomaly had truly been a mistake in how the map was cleaned, it should have looked noticeably different when viewed through Planck's far more capable instruments. Instead, the signal remained remarkably consistent from one generation of satellite to the next. Before we go further into what happened after Planck, it is worth taking a slower look at the specific arguments skeptics raised against the axis of evil, because they represent some of the most careful, technical thinking in modern cosmology, and because understanding them helps explain just how much weight the eventual confirmation actually carries. The most prominent argument against the reality of the axis is known as foreground contamination. The cosmic microwave background is the oldest light in the sky, but in order to see it, our satellites have to look straight through everything sitting between us and the edge of the observable universe. The biggest obstacle by far is our own galaxy. The Milky Way is a busy, dusty, and energetic place. It emits its own radiation in a variety of forms, including synchrotron emission, which comes from high-speed electrons spiraling around magnetic field lines, and thermal emission from warm dust and star-forming regions. In order to produce the clean, pristine maps of the cosmic microwave background that appear in textbooks, scientists must carefully model and subtract all of this galactic noise. This process is often called cleaning the map. If that subtraction is even slightly imperfect, some of the geometry of our own galaxy can leak into what is supposed to be a map of the distant universe. because the Milky Way itself sits on roughly the same general plane as our solar system. Any leftover signal from this leakage would naturally tend to align with the ecliptic, creating a false pattern that mimics a genuine cosmic axis, when in reality it is just poorly subtracted dust from our own galactic backyard. A second technical concern involves the way scientists account for our own motion through space. As mentioned earlier, our solar system is moving relative to the cosmic microwave background at around 370 kilometers per second. This motion produces a large dipole signal, making one side of the sky look warmer and the other cooler. While removing this dipole is a relatively well-understood procedure, an imperfect correction can produce a secondary distortion sometimes called a kinetic quadrupole. If the mathematics used to correct for our own motion is not applied with perfect precision, it can subtly distort the larger scale multipoles, potentially nudging the quadrupole and the octupole into an alignment that looks real, but is actually an artifact of the correction process itself. There is also the problem of masking, because the central band of our own galaxy is so bright, densely packed with stars, gas, and dust. Cosmologists are forced to place a mask over that portion of the sky, essentially instructing their analysis to ignore those particular pixels entirely, since no meaningful cosmic microwave background signal can be recovered from underneath such intense galactic emission. However, cutting a large hole out of the middle of any dataset inevitably changes its statistical properties in subtle ways. Critics have argued that the specific shape of the mask used in these analyses might itself be distorting the multipole calculations, effectively squeezing the mathematics in a way that produces a fake alignment, an artifact of the reconstruction process rather than a genuine feature of the sky. Finally, there is a broader statistical principle worth mentioning, sometimes called the look elsewhere effect. This is the simple observation that if you examine a large enough data set for long enough, searching across enough possible patterns, you will eventually stumble upon something that looks statistically impossible purely by chance. The human brain, after all, is remarkably good at finding patterns, sometimes even where none genuinely exist. Skeptics have pointed out that if the axis had instead aligned with, say, the galactic North Pole or the orbital path of the Moon, or some other arbitrary direction, we might still be calling it a miraculous coincidence. In other words, perhaps we have simply cherry-picked one unusual alignment out of thousands of possible statistical flukes, buried within an enormously complex data set, and mistaken ordinary randomness for a deep cosmic mystery. These are all serious, carefully reasoned objections, and for years they provided a reasonable and comfortable explanation for the axis of evil. But as we will see, when Planck arrived with entirely different instruments, different frequency channels, and improved cleaning methods, and the same alignment persisted anyway, these explanations became considerably harder to sustain. The confirmation from Planck shifted the scientific conversation in an important way. Before Planck, the central question had been simple: is this a mistake? After Planck, the question became more unsettling. If it is not a mistake, then what exactly is the universe trying to tell us? This shift pushed researchers toward a more rigorous type of test, one involving not just the temperature of the cosmic microwave background, but its polarization as well. Most of the familiar images of the cosmic microwave background that circulate in documentaries and textbooks are temperature maps, showing tiny variations in heat scattered across the whole sky. But the ancient light also carries a second kind of information called polarization. As photons scattered off free electrons in the hot, dense plasma of the early universe, certain physical processes imparted a specific orientation or twist to the light itself. This is known as E-mode polarization, and it arises from the same basic physics that governs how sunlight becomes polarized when it reflects off water or glass. Though on an almost unimaginably larger scale and much earlier in cosmic history, the logic behind using polarization as a test is fairly straightforward, even if the underlying physics is subtle. If the axis of evil represents a genuine physical feature of the geometry of the universe, something baked into the actual structure of space itself, then it should show up in the polarization data just as clearly as it does in the temperature data. If, on the other hand, the alignment only ever appears in the temperature maps and vanishes when you examine polarization, that would strongly suggest the whole thing is a statistical fluke, or perhaps some very specific and localized form of interference that only affects one type of measurement. By around 2024 and 2025, advanced analyses of the Planck polarization data have begun reaching the wider scientific community, and the results, by most honest accounts, have been frustratingly ambiguous. Some research teams reported that the polarization data does appear to show a preferred direction that roughly matches the temperature-based axis. If accurate, this would suggest that whatever caused the alignment was present at the very moment the light itself was released, long before our solar system had even begun to form. Other research groups, however, have argued that the signal-to-noise ratio in the polarization maps remains too low to draw firm conclusions, because the polarization signal of the cosmic microwave background is inherently much weaker than the temperature fluctuations. Even small errors or residual contamination can more easily mask the true underlying pattern. This disagreement has led to a genuine and ongoing split within the cosmology community. One camp argues that the persistence of the axis across two entirely different satellite missions and across multiple distinct types of measurement amounts to a compelling case for genuinely new physics. The other camp maintains that we are still dealing with a subtle statistical anomaly, one that more precise future measurements will eventually explain away. What makes this particular chapter of the story so important is that it eliminates many of the easy answers that once seemed available. We can no longer simply blame a faulty sensor aboard the WMAP satellite. We can no longer wave the whole thing away as a simple smear of poorly subtracted galactic dust. The Planck mission demonstrated, convincingly, that the axis of evil is a robust and repeatable feature of our current maps of the universe. Observed independently, using different hardware, different frequencies, and different cleaning techniques, this leaves cosmologists with an uncomfortable choice. Either our statistical methods are failing us in some very specific and stubborn way that has so far eluded detection, or the universe truly is not the smooth, uniform, directionless place we have long assumed it to be. For years, the strongest argument in favor of the axis being nothing more than an unlucky coincidence was its apparent isolation. Skeptics reasonably pointed out that if the universe truly had a preferred direction woven into its structure, we should expect to see hints of that bias showing up somewhere else too, not just in one particular analysis of one particular kind of ancient light. If the very fabric of space really is lopsided in some subtle way, that bias ought to leave fingerprints on the motion of galaxies, on the orientation of large-scale structures, and on other independent measurements entirely unrelated to the cosmic microwave background by around 2024 and 2025. That argument from isolation began to weaken considerably as several independent lines of evidence started, pointing in strikingly similar directions. The first significant piece of supporting evidence involves a phenomenon known as dark flow. By carefully studying something called the kinetic Sano-Zeldovich effect, which describes how photons from the cosmic microwave background get subtly kicked in energy as they pass through hot gas surrounding distant galaxy clusters, astronomers uncovered something rather baffling. Thousands of galaxy clusters, separated from one another by truly enormous distances, appeared to be moving coherently at significant speeds toward one particular, fairly specific patch of the sky. Crucially, this motion could not be explained by the ordinary expansion of the universe, nor could it be attributed to the gravitational pull of any known concentration of mass within our observable horizon. It appeared to be a genuinely coherent, large-scale flow, one that suggested something lying beyond our observable universe might be, exerting a gentle gravitational pull on the matter within it. What made this discovery especially intriguing is that the general direction of this dark flow turned out to be roughly consistent with the direction of the axis of evil found in the cosmic microwave background. This raised the possibility that the alignment was not merely a pattern locked into the temperature of ancient light, but potentially a real physical characteristic reflected in how matter itself moves through the modern universe. If galaxies really are being gently pulled in a particular preferred direction, that would imply the universe genuinely is not the same in every direction, undermining the basic assumption of isotropy that the standard cosmological model depends upon. The picture grew even more complex with the arrival of massive new surveys of quasars, which are the extraordinarily bright centers of distant galaxies, powered by supermassive black holes actively feeding on surrounding gas and dust. Because quasars are visible across truly vast cosmic distances, spanning billions of light years, they serve as useful markers for tracing the large-scale structure of the universe. In a series of studies conducted between roughly 2022 and 2025, researchers examining the spin axes of large populations of these quasars found that their orientations were not distributed randomly, as the standard model would predict. Instead, the spin axes appeared to align with one another across distances spanning billions of light years. Even more remarkable, these quasar alignments seemed to trace out a pattern that roughly matched the same large-scale direction indicated by the cosmic microwave background axis. There is no conventional physical mechanism that would cause a supermassive black hole in one distant corner of the universe to align its spin with another black hole in a completely different corner, unless both were somehow influenced by a shared underlying grain in the geometry of space itself. When researchers began combining the cosmic microwave background data, the dark flow measurements, and the quasar alignment studies, the statistical likelihood of all three independently pointing in roughly the same direction, purely by chance, dropped to something vanishingly small. This convergence of evidence from entirely separate physical phenomena is sometimes described as a multi-messenger crisis, a nod to the idea that we are no longer looking at a single strange feature in a single satellite's map, but rather a consistent directional bias appearing across the temperature of the earliest light in the universe, the coordinated motion of modern galaxy clusters, and the orientation of some of the most ancient black holes we can observe. If these independent measurements really are all reflecting the same underlying phenomenon, then the axis of evil begins to look less like a ghost hiding somewhere in our instruments, and more like the first tangible evidence that the universe possesses some kind of genuine preferred orientation. It raises the unsettling possibility that the perfect uniformity cosmologists have assumed for the better part of a century might, in fact, be something closer to a local illusion, one that breaks down once you examine large enough scales, revealing a structured, directional universe that we are only just beginning to properly map. The reason the axis of evil unsettles so many cosmologists is that it does not exist in isolation from the rest of modern cosmology's troubles. It is part of a broader, growing list of tensions and anomalies, suggesting that our standard model of the universe, lambda cold dark matter, may be running into serious trouble. For decades, Cosmologists have relied on a particular family of equations known as the Friedmann-Lamar-Robertson-Walker metric, developed in the early decades of the 20th century by several independent researchers working on how general relativity applies to an expanding universe. This mathematics forms the backbone of nearly everything we understand about the Big Bang and the subsequent evolution of the cosmos. But it depends on two non-negotiable assumptions: that the universe looks the same in every direction, and that it looks the same from every location. If the axis of evil turns out to be a genuine physical feature of our universe, both of those assumptions come under direct and serious threat. This brings us to one of the most heavily discussed puzzles in modern astronomy, known as the Hubble tension. For many years now, different methods of measuring the rate at which the universe is expanding, a number known as the Hubble constant, have produced stubbornly different results. When researchers measure the expansion rate using the cosmic microwave background, working backward from the physics of the early universe, they arrive at one particular value. When other researchers measure the expansion rate more directly, using nearby stars called Cepheid variables to calibrate the distances to more distant exploding stars, called Type 1 a supernova, building what is known as the cosmic distance ladder, they arrive at a noticeably higher value. For a long time, most cosmologists assumed this discrepancy was simply the result of measurement error, something that more careful observations would eventually resolve. But as of 2026, after well over a decade of increasingly precise measurements from multiple independent teams and instruments, the gap between these two values has not closed. If anything, it has grown more statistically significant. There is a growing school of thought suggesting that the Hubble tension and the axis of evil may actually be two separate symptoms of the very same underlying problem. If the universe genuinely does possess a preferred direction or some kind of large-scale lopsided structure, then it becomes entirely plausible that the expansion rate itself is not perfectly uniform everywhere. We might, in this scenario, be living within some kind of unusually large, relatively underdense region of space, one that happens to be expanding at a slightly different rate than the cosmic average. If our calculations of the age and expansion history of the universe are built on the assumption that everything is perfectly uniform, but in reality, we are sitting somewhere near a subtle directional or structural anomaly, our numbers would never be expected to match cleanly, no matter how precisely we measure them. Under this view, the axis of evil provides the directional piece of evidence, while the Hubble tension provides the corresponding evidence of an inconsistent expansion rate. Together, they suggest that the standard cosmological model may be, at best, a useful oversimplification of a considerably more complicated underlying reality. It is worth pausing here to place these puzzles within the broader landscape of large-scale structure, because the axis of evil is not the only hint that the universe might be less uniform than textbooks have traditionally suggested. Surveys of galaxies conducted over the past 2 decades have revealed a series of enormous structures that challenge our intuitive sense of cosmic homogeneity. There is, for instance, an unusually large underdense region sometimes called the local void, or in some analyses the KBC void, named after the researchers who mapped it, spanning hundreds of millions of light years and possibly influencing local measurements of the expansion rate. There are also vast filamentary structures, sometimes informally described as great walls, stretching for billions of light years across the observable universe. Structures so large that some researchers have questioned whether they are even compatible with the assumption that the universe becomes smooth and uniform on sufficiently large scales. None of these individual pieces of evidence proves, on its own, that the standard cosmological model is wrong. But taken together, they paint a picture of a universe considerably more textured, more structured, and perhaps more surprising than the smooth, featureless cosmos many of us grew up learning about. All of this forces a confrontation with the philosophical heart of the Copernican principle itself. If researchers eventually determine that the large-scale structure of the universe genuinely aligns in some meaningful way with the orientation of our own solar system, cosmologists are faced with a possibility that many find deeply uncomfortable. We would have to seriously entertain the idea that our position in the universe is not, in fact, average or unremarkable. Some theorists have proposed, only half seriously in some cases, that we might happen to be located near the center of an enormous cosmic void, and that in such a scenario, the apparent axis would not represent some intrinsic property of the entire universe, but rather an artifact of how light happens to travel through the particular, unusually empty patch of space surrounding us. Accepting this kind of explanation, however, would require abandoning the comfortable assumption that the laws of physics and the general appearance of the cosmos are truly identical everywhere. It would mean accepting that what we observe from Earth might be, in some subtle sense, a special or unusual case, rather than a universal, generic truth about the cosmos as a whole. For roughly 4 centuries, the entire progression of scientific thought has moved steadily away from the idea that we occupy any kind of special or privileged position in the universe. To suggest, even tentatively, that the large-scale structure of the cosmos might somehow be tied to our specific coordinates in space fields, to many scientists, uncomfortably close to a step backward, back toward the pre-scientific geocentric worldview that placed Earth at the very center of creation. This is part of why the debates surrounding the axis of evil carry such emotional and philosophical weight within the scientific community. It is not merely a disagreement over a few data points scattered across a map. It touches on whether one of the central guiding philosophies of the entire scientific method, the assumption that we are not special, remains fully valid. If the Copernican principle does eventually turn out to be incomplete in some meaningful way, the lambda cold dark matter model would effectively become a local approximation, valid perhaps only in our particular corner of the universe, rather than a truly universal description of the cosmos as a whole. Physicists would need to develop an entirely new theoretical framework, one capable of accounting for genuine anisotropy, a universe possessing some kind of grain, flow, or persistent lopsidedness built into its fundamental structure. In many ways, cosmology currently finds itself in a period that historians of science sometimes call crisis science, a phase where the old theoretical framework no longer cleanly explains everything we observe, while the new framework needed to replace it has not yet been fully written. The axis of evil stands as perhaps the most visible and puzzling signpost currently pointing toward that uncertain, unwritten future. Given how seriously cosmologists take this puzzle, it is worth spending some time on the range of theoretical explanations currently being explored, each of which attempts to account for the alignment without abandoning modern physics altogether. The most conservative class of explanations falls under the heading of non-trivial topology. In the standard cosmological model, we typically assume that the universe is either infinite in extent, or so enormously large that its overall shape becomes essentially irrelevant to any observation we could ever make. However, it remains mathematically possible that the universe is actually finite in size, while still having no detectable edge or boundary, somewhat analogous to the surface of a 3-dimensional donut shape, technically referred to as a 3 torus. In a universe shaped this way, if you were to travel far enough in a single direction, you would eventually loop back around and arrive back where you started, much like walking in a straight line across the surface of a sphere. This kind of wraparound geometry would mean that light emitted near the beginning of the universe could, in principle, take multiple distinct paths to eventually reach us, effectively echoing around the overall shape of the cosmos multiple times before arriving at our telescopes. If this geometry is even slightly asymmetric, narrower along one dimension than another, it would naturally tend to create a preferred direction in the resulting temperature patterns of the cosmic microwave background, potentially explaining the observed alignment between the quadrupole and the octupole. Interestingly, this general family of ideas is not entirely new. In the years immediately following the original WMAP discovery, some researchers proposed a related idea involving a dodecahedral, or 12-sided, finite universe, and searched for matching circles in the cosmic microwave background sky that would reveal such a wraparound structure. Though that particular search ultimately came up empty, more recent simulations conducted around 2025 have shown that certain 3 torus topologies can reproduce the observed quadrupole and octupole alignment remarkably well, all without requiring us to occupy any kind of special or privileged location within the universe. A more radical category of explanation moves beyond the shape of the universe and questions the underlying mathematical framework used to describe space and time altogether. For more than a century, general relativity has relied on a branch of mathematics called Riemannian geometry, which assumes that the fundamental properties of space remain identical regardless of which direction you happen to be facing. An alternative and considerably more complex mathematical framework, called Finsler geometry, allows for genuine anisotropy to be built directly into the fabric of space-time itself. In a universe governed by Finslerian rather than Riemannian geometry, quantities like the effective speed of light or the local strength of gravity could, in principle, vary very slightly depending on your orientation within space. While this idea sounds genuinely radical and remains firmly outside the mainstream of theoretical physics, it would offer a natural explanation for why we might observe a consistent preferred direction across multiple independent phenomena, from the cosmic microwave background to the motion of galaxy clusters, to the spin orientation of distant quasars. Under this framework, the grain we appear to be detecting would not represent an error in our maps or our methods, but rather a genuine fundamental property woven into the underlying vacuum of space itself. A newer, and in many ways more provocative, theoretical frontier involves what is sometimes called the holographic projection hypothesis, an idea that gained considerable traction within parts of the theoretical physics community around 2025. This general framework, which traces its origins back to earlier theoretical work connecting gravity and quantum information theory, suggests that our familiar three-dimensional universe might be best understood as a kind of projection of information, fundamentally stored on a distant two-dimensional boundary, situated at the very edge of observable space. Under this model, the axis of evil would not represent an actual physical line running through space, but rather something closer to an optical artifact, produced by our particular position and orientation relative to that distant informational boundary. It has sometimes been compared to how a person, standing inside a room containing a large holographic display, might perceive shifting patterns that appear to align or realign depending on exactly where they stand and which direction they happen to be facing. If some version of this hypothesis eventually proves correct, the axis of evil could represent one of the first tangible pieces of observational evidence connecting the enormous, large-scale world of cosmology to the strange, counterintuitive microscopic world of quantum information theory. Finally, there remains the more traditional theory of primordial magnetism. Some researchers argue that in the earliest fraction of a second following the Big Bang, the entire universe may have been permeated by an enormous, coherent magnetic field, generated by processes that are still not fully understood, sometimes grouped together under the general term magnetogenesis. Such a field would have acted almost like an invisible physical scaffold, subtly guiding the flow of the hot, dense plasma that filled the early universe, and influencing the formation of the very first cosmic structures. Because magnetic fields inherently possess a north pole and a south pole, they naturally create a preferred axis wherever they exist. A sufficiently strong primordial magnetic field could have left a lasting imprint on the pattern of the cosmic microwave background, and might have gone on to influence the rotational orientation of galaxies forming throughout the history of the universe. Each of these very different theoretical approaches, whether it involves the overall shape of the universe wrapping back on itself, a fundamental grain built into the mathematics describing gravity, an ancient magnetic field steering the formation of cosmic structure, or a holographic trick of perspective, shares a common underlying goal. Each is an attempt to find a genuine physical explanation for the observed alignment, one that does not require abandoning the broader framework of modern physics entirely, and one that does not require invoking anything resembling a miracle before moving toward the current state of the search. It is worth taking a moment to remember how this entire field of study came into existence in the first place, because the story of the cosmic microwave background itself is, in its own right, a remarkable piece of scientific history. The existence of this ancient radiation was first predicted theoretically in the 1940s by researchers including Ralph Alpher, Robert Herman, and George Gamow, working through the implications of a hot, dense early universe cooling over billions of years. Their prediction, however, went largely unnoticed for nearly 2 decades. It was not until 1965 that 2 radio astronomers, Arno Penzias and Robert Wilson, working at Bell Laboratories in New Jersey, accidentally detected a persistent, faint background hiss in their radio antenna, a signal they initially assumed must be some kind of instrumental defect, possibly even caused by pigeon droppings accumulating inside their equipment. After carefully ruling out every conceivable source of local interference, they eventually realized they had stumbled upon the actual afterglow of the Big Bang itself, a discovery that would later earn them the Nobel Prize in Physics. For more than 2 decades afterward, cosmologists worked to build increasingly sensitive instruments capable of mapping this faint, ancient light with ever greater precision. The Cosmic Background Explorer satellite, usually known as COBE, launched by NASA in 1989, provided the first definitive detection of the tiny temperature fluctuations scattered across the cosmic microwave background, fluctuations representing the seeds from which all future cosmic structure would eventually grow. This discovery was significant enough to earn its own Nobel Prize in Physics, awarded to researchers John Mather and George Smoot in the early 2000s. Building on that foundation, the Wilkinson Microwave Anisotropy Probe, launched in 2001, provided a far more detailed and precise map of these fluctuations, refining our understanding of the age, composition, and geometry of the universe with remarkable accuracy. It was this same instrument that, in 2005, first revealed the strange alignment that would eventually come to be known as the axis of evil. Understanding this long history helps clarify why the eventual confirmation by the Planck satellite carried so much scientific weight. Each successive generation of instruments represented a genuine leap forward in sensitivity, precision, and reliability. The fact that an unusual, seemingly anomalous pattern first glimpsed by an early generation instrument persisted, essentially unchanged, through multiple subsequent generations of far more capable technology, is precisely the kind of evidence that transforms a curious anomaly into a serious scientific puzzle demanding a genuine explanation. As of 2026, The scientific community finds itself at something of a genuine crossroads. The standard model of cosmology, which has faithfully guided our understanding of the universe for well over a generation, appears to be missing some important piece of the overall picture. We seem to be looking at a universe that is considerably more structured and perhaps considerably more eccentric than our existing theoretical framework was originally designed to accommodate. If the axis of evil truly is a physical, measurable reality, it may well signal the end of an era in which the universe was assumed to be an entirely generic, unremarkable, uniform expanse of space. It suggests, instead, that the cosmos we inhabit possesses a specific underlying geometry, a specific large-scale flow, and quite possibly a specific overall orientation, one that we are only just now beginning to properly measure and understand. This growing body of evidence forces a genuine shift in how we think about our own place within the cosmos. For centuries, scientific progress has meant steadily removing ourselves from the center of the story, pushing Earth further and further away from any position of cosmic importance. Yet if the largest observable structures in existence really do turn out to be aligned, in some meaningful physical sense, with the specific orientation of our own solar system, we find ourselves confronting a genuine mystery, one that edges right up against the philosophical. It does not necessarily imply that the universe was somehow designed with us specifically in mind, but it does suggest, at the very least, that our particular corner of the cosmos might be linked, in some way we do not yet fully understand, to the broader architecture of the universe as a whole. Whether that underlying link eventually turns out to be the result of the universe's overall shape wrapping back on itself, some kind of holographic projection effect, or simply the consequence of our being located within an unusually large, relatively empty local void, the practical result remains largely the same. The Copernican principle, at least in its simplest and most literal form, may no longer be entirely sufficient to describe the full reality of our universe. Fortunately, we are not simply left waiting indefinitely for an answer. Several new missions and instruments are currently being developed and refined, specifically to search for a more definitive resolution to this ongoing puzzle. The Light BIRD satellite, a Japanese-led mission currently in development, along with ground-based observatories such as the Simons Observatory, located high in the Atacama Desert of Chile, are being carefully tuned to search for an extremely faint signal known as B-mode polarization, an especially subtle pattern within the cosmic microwave background that could provide much stronger, more direct evidence regarding the earliest moments of the universe, including possible clues about primordial magnetic fields and the detailed physics of cosmic inflation itself. These next-generation instruments are being engineered with unprecedented sensitivity, specifically designed to see through the remaining layers of galactic dust and noise with far greater clarity than any previous mission. In time, they should be capable of definitively confirming whether the axis of evil represents a genuine physical property of the vacuum of space itself, or whether it will finally be revealed, after more than 2 decades of careful investigation, to be the most elaborate and persistent statistical illusion in the history of modern cosmology. Until that final determination arrives, the axis of evil remains something of an open scar on our current map of the universe, a persistent reminder that science is never truly settled, and that the cosmos remains under no particular obligation to be simple, symmetric, or even fully logical according to our own comfortable expectations. We began this particular scientific journey looking for nothing more than a random, formless afterglow left behind by an ancient cosmic explosion. Instead, across 2 decades of increasingly careful measurement, we appear to have stumbled upon something that behaves suspiciously like a compass needle, quietly pointing toward a very specific direction in the sky. Whether that needle ultimately points us toward a genuinely new chapter in fundamental physics, or toward some deeply hidden flaw in our own methods of perception and measurement, remains, for now, one of the great open questions of contemporary cosmology. We are, in a very real sense, no longer simply passive observers gazing out at a uniform, featureless sea of distant stars and galaxies. We have become active explorers of a cosmos that may well possess a genuine direction, a genuine large-scale structure, and perhaps even a quiet and ancient secret, one written faintly across the sky in the very oldest light we are capable of seeing. And for now, that is where the story rests. Unresolved, patient, waiting for better instruments, more careful measurements, and a bit more time to reveal exactly what it is trying to tell us. Let us take a slower walk through some of the broader, scientific landscape surrounding this puzzle. Because the axis of evil did not appear in a vacuum, so to speak. It emerged from decades of careful, patient work mapping the sky, refining instruments, and slowly building confidence in a standard picture of the universe that until relatively recently seemed remarkably successful. The standard model of cosmology rests on three broad pillars, each supported by an enormous body of independent evidence. The first pillar is the expansion of the universe itself, first firmly established observationally in the late 1920s by the astronomer Edwin Hubble, working at the Mount Wilson Observatory in California. Hubble noticed that distant galaxies were almost universally moving away from us, and that the further away a galaxy happened to be, the faster it appeared to be receding. This relationship, now known as Hubble's law, provided the first solid observational evidence that the universe itself is expanding, a finding that would eventually lead back, through careful extrapolation, to the concept of a hot, dense beginning, the Big Bang itself. The second pillar is the abundance of light elements observed throughout the universe, particularly hydrogen, helium, and small trace amounts of lithium. The theory of Big Bang nucleosynthesis predicts, with remarkable precision, exactly how much of each of these elements should have been produced during the first few minutes after the Big Bang, based on the temperature and density of the early universe. Observational measurements of these elemental abundances, gathered from careful study of ancient, pristine gas clouds relatively untouched by later stellar processes, match these theoretical predictions closely, providing strong independent support for the overall Big Bang framework. The third pillar, of course, is the cosmic microwave background itself, the faint afterglow whose subtle patterns we have been discussing throughout this exploration. The overall pattern of temperature fluctuations observed across the cosmic microwave background matches, with extraordinary precision, the predictions of the standard cosmological model, allowing researchers to determine the age of the universe, its overall composition in terms of ordinary matter, dark matter and dark energy, and the general geometry of space itself, all with remarkable accuracy. Given how successful this standard framework has been, it is worth appreciating just how disruptive genuine anomalies, like the axis of evil or the Hubble tension, can feel to researchers who have spent entire careers building and refining this particular picture of the cosmos. These are not fringe ideas dismissed by the mainstream community. They are puzzles actively discussed, debated, and investigated by some of the most respected cosmologists currently working in the field, published in leading peer-reviewed journals, and presented at major international conferences. It is also worth spending a little more time on the broader context of large-scale structure surveys, since they provide an important complementary perspective to the cosmic microwave background studies we have focused on so far. Modern galaxy surveys, using large ground-based telescopes equipped with wide-field cameras and spectrographs, capable of measuring the precise distances to hundreds of thousands, and in some cases millions of individual galaxies, have revealed an intricate cosmic web of filaments, sheets, and voids stretching across the observable universe. Galaxies are not scattered randomly throughout space. Instead, they cluster together along enormous filamentary structures, sometimes stretching for hundreds of millions of light years, separated by vast, relatively empty voids of similarly staggering size. This cosmic web represents the natural outcome of gravity slowly amplifying the tiny density fluctuations first imprinted during the earliest moments of the universe. Fluctuations we can still see, frozen in place, within the cosmic microwave background itself. Some particularly large structures identified within these surveys have themselves generated considerable scientific debate, since their sheer size occasionally strains the theoretical limits of how large any single structure should be able to grow. Given the age of the universe and the standard rules governing the growth of cosmic structure through gravity alone. While these individual structures do not, on their own, definitively prove that the standard cosmological model is incorrect, they do contribute to a broader sense that our universe might be considerably more textured, more structured, and occasionally more surprising than the relatively smooth, idealized cosmos often portrayed in introductory textbooks and popular science documentaries. Taken as a whole, then, the picture that emerges is neither one of definitive crisis nor one of complete reassurance. It is, instead, a genuinely open and actively evolving area of scientific investigation, one where careful, patient measurement gradually accumulates evidence, where competing theoretical explanations are proposed, tested, and refined, and where definitive answers often take considerably longer to arrive than any of us might prefer. The axis of evil remains, for now, a genuinely unresolved mystery, one thread among several within the broader tapestry of modern cosmological anomalies, each pointing toward the same underlying possibility that our current understanding of the universe, however successful it has been, may still be missing some deeper, more complete picture, one that future generations of instruments and future generations of careful, patient scientists will eventually help bring more fully into focus. For now, we can simply sit with the mystery itself, the way you might sit quietly with any large, unanswered question late at night, comfortable in not needing an immediate resolution. The universe, it turns out, is under no particular obligation to reveal all of its secrets quickly, or neatly, or in ways that conveniently match our existing expectations. It reveals them slowly, patiently, one careful measurement at a time, across generations of researchers, instruments, and quiet, careful nights spent studying the faint ancient light still arriving from the very edge of time itself. And so, for tonight, we leave the axis of evil exactly where it currently sits. An open, gently glowing question mark, hovering faintly over an otherwise familiar night sky, waiting patiently for its answer. It helps, at this point, to slow down and walk back through how the cosmological principle came to occupy such a central place in physics in the first place, because it did not arrive fully formed. It grew slowly, out of necessity, as much as out of observation. When Albert Einstein first applied his newly developed equations of general relativity to the universe as a whole. Back in the 1910s, he ran into an uncomfortable problem. His equations, applied honestly, predicted that the universe could not simply sit still. Gravity, pulling everything inward, should cause a static universe to collapse in on itself. At the time, nearly everyone, including Einstein, assumed the universe was static, eternal, and unchanging, since that was simply how the night sky appeared to behave, one year after another, one century after another. To force his equations to describe a stable, unmoving universe, Einstein introduced an extra term into his equations, a kind of repulsive counterbalance he called the cosmological constant, purely to hold everything in place. He would later reportedly describe this move as one of the greatest blunders of his career, though modern cosmologists have since come to see that same term in a strikingly different light, as we will return to shortly. Around the same period, a Dutch astronomer named Willem de Sitter found a different solution to Einstein's equations, one describing an expanding, nearly empty universe. A Russian physicist named Alexander Friedman, working independently, found a broader family of solutions allowing for universes that could expand, contract, or hover at some delicate balance point, depending on their overall density. A Belgian priest and physicist named Georges Lemaître arrived at similar conclusions independently, and was among the first to propose that the universe had originated from an extremely dense, hot initial state, an idea that would eventually evolve into what we now call the Big Bang Theory, though that particular name was originally coined somewhat dismissively by a skeptic of the idea. It was Edwin Hubble's observational work in the late 1920s, measuring the distances and recession velocities of distant galaxies using the Large Telescope at Mount Wilson, that finally settled the argument in favor of an expanding universe. Once astronomers accepted that the universe was expanding, the cosmological principle, the assumption that this expansion looks the same in every direction and from every location, became less a philosophical preference and more a practical necessity. Without it, the equations describing an expanding universe become vastly more complicated, requiring detailed knowledge of the exact distribution of matter and energy at every point in space, an impossible task given what could actually be observed. Assuming uniformity allowed physicists to write down a single, elegant, solvable set of equations describing the entire history of the cosmos, from its earliest moments through to the present day. That elegant simplicity is part of why the cosmological principle has proven so difficult to give up, even in the face of anomalies like the axis of evil. An enormous amount of modern cosmology, spanning nearly a century of careful theoretical work, rests on the mathematical convenience that uniformity provides. This history also explains why cosmologists reacted with such caution when the original WMAP alignment was first announced back in 2005. It was not simply institutional stubbornness or resistance to new ideas. Abandoning strict isotropy would mean rewriting large sections of the theoretical framework that has successfully described the universe for the better part of a century. A framework that correctly predicted the abundance of light elements, correctly predicted the existence and detailed pattern of the cosmic microwave background itself, and correctly predicted the large-scale distribution of galaxies observed in modern surveys. Any replacement theory would need to preserve all of those successes while also explaining the new anomalies. A genuinely difficult scientific challenge. Let us return for a moment to the dark flow measurement, because its own history is worth understanding in a bit more detail. The astronomer Alexander Kashelinski and his collaborators first proposed the existence of this coherent, large-scale motion back in 2008, using early data from WMAP combined with catalogs of galaxy clusters. Their method relied on the kinetic Sunna-Zeldovich effect, a subtle physical process first described theoretically in the late 1960s and early 1970s by the Soviet physicists Rashid Sunyaev and Yakov Zeldovich. The effect works roughly like this. Galaxy clusters are filled with enormous clouds of extremely hot ionized gas. As photons from the cosmic microwave background pass through this hot gas on their way to us, a small fraction of them scatter off the free electrons contained within it. If the galaxy cluster itself is moving relative to the cosmic microwave background, this scattering process imparts a tiny characteristic shift to the energy of the scattered photons, slightly boosting or slightly reducing their apparent temperature depending on the direction and speed of the cluster's motion. By carefully measuring this subtle energy shift across thousands of individual galaxy clusters, Kashalinsky and his colleagues were able to reconstruct a kind of large-scale velocity map, revealing that a substantial fraction of the observable universe appeared to be streaming coherently in one particular direction, at speeds of several hundred kilometers per second, a scale of coherent motion not easily explained by any known gravitational source within our observable horizon. The original 2008 measurement generated considerable controversy at the time, with several independent research groups questioning whether the statistical methods used had properly accounted for all sources of noise and systematic error. Subsequent studies, using improved data from Planck and various ground-based telescopes, have continued to debate the exact magnitude and statistical significance of the effect. Though the general consensus among researchers actively working on the problem has shifted gradually toward accepting that some genuine large-scale coherent flow likely does exist, even if its precise magnitude, extent, and ultimate physical cause remain matters of active investigation. What makes the story relevant to our broader discussion tonight is simply the rough directional consistency between this independently measured flow and the axis identified within the cosmic microwave background itself, a consistency that on its own would mean little, but which gains considerable weight when combined with the additional quasar alignment evidence gathered more recently. The quasar studies themselves deserve a slightly closer look as well, since the underlying methodology is genuinely clever. Quasars, being among the most luminous objects in the universe, can be observed and catalogued across truly enormous distances, allowing astronomers to build maps encompassing many hundreds of thousands of individual objects spread across large fractions of the observable universe. Measuring the spin axis of a supermassive black hole directly is, of course, impossible using current technology, since these objects are far too small and far too distant to resolve directly. Instead, researchers infer the orientation of a quasar's spin axis indirectly, typically by studying the polarization of the light emitted from the accretion disk and jet structures surrounding the central black hole. Structures whose observed orientation on the sky reflects the underlying spin axis of the central object itself. When researchers compiled large catalogs of these inferred spin orientations across different regions of the sky, several independent teams reported a statistically significant tendency for neighboring quasars, even those separated by enormous distances, to display correlated spin orientations, rather than the fully random distribution predicted by standard models of galaxy formation. Some of the most extensive of these analyses, conducted using data gathered between roughly 2022 and 2025 from a combination of ground-based and space-based observatories, found that this correlated alignment pattern traced out large-scale structures in a way that roughly, though not perfectly, matched the general direction indicated by both the cosmic microwave background axis and the separately measured dark flow dot. It is worth being honest about the limitations of this particular line of evidence as well. Measuring the precise spin orientation of any individual quasar carries significant observational uncertainty, and different research teams have sometimes used somewhat different statistical methods to search for large-scale alignment patterns within their respective catalogs, occasionally arriving at moderately different conclusions regarding the exact strength and statistical significance of the effect. Nonetheless, the general trend across multiple independent studies has continued to point in a broadly consistent direction, adding one more thread to the broader tapestry of evidence suggesting that our universe may possess some genuine large-scale anisotropic structure beyond what the standard cosmological model currently predicts. There is yet another, somewhat older line of evidence worth mentioning here as well. One that predates even the original WMAP discovery of the axis of evil. Since the late 1990s, some researchers studying the polarization of radio waves emitted by extremely distant radio galaxies have reported hints of a subtle, systematic rotation in the polarization angle of this light, one that appears to depend on the particular direction of the sky being observed, a phenomenon sometimes referred to informally as cosmic birefringence. If real, this effect would suggest that the vacuum of space itself behaves slightly differently depending on direction, potentially connecting to some of the exotic theoretical frameworks we discussed earlier, including Finsler geometry and certain models involving primordial magnetic fields or new fundamental particles interacting weakly with light. This particular line of evidence remains, even today, considerably more contested and statistically uncertain than the CMB alignment or the quasar studies. But it represents yet another example of researchers working entirely independently and using entirely different types of astronomical data, stumbling upon hints of a preferred direction somewhere within the observable universe. Given how many independent lines of evidence now appear to point in roughly similar directions, it becomes useful to step back and ask what the broader scientific community currently makes of all this. Taken together, as of 2026, the honest answer is that opinions remain genuinely divided, and reasonably so. A meaningful fraction of working cosmologists continue to view each of these individual anomalies as most likely representing subtle, as yet unidentified systematic errors, various forms of residual contamination, or simple statistical flukes that happen to have survived multiple rounds of increasingly careful scrutiny, largely due to chance. This is not an unreasonable position. Science has a long history of anomalies that eventually resolved themselves once sufficiently careful follow-up work was completed. And cosmology in particular has weathered numerous false alarms over the decades. Historical results that seemed, at the time, to threaten the standard model, but which were later traced back to previously unrecognized instrumental effects or subtle analysis errors. A second, growing fraction of the community has become increasingly convinced that something genuinely new is going on, though there remains considerable disagreement even among this group regarding which theoretical explanation is most likely correct. Some favor relatively conservative explanations, such as non-trivial cosmic topology or an unusually large local void, explanations that would require relatively modest adjustments to existing theory. Others find themselves drawn toward more radical possibilities, involving fundamentally anisotropic geometry, holographic explanations, or entirely new physics operating at scales and energies, while beyond anything current particle accelerators can probe directly. It is worth mentioning, too, how this entire discussion connects to the separate but related puzzle of dark energy, the mysterious component believed to be driving the accelerating expansion of the universe. First discovered through careful observations of distant supernova in the late 1990s. The nature of dark energy remains one of the single largest unsolved problems in modern physics. And in recent years, results from the Dark Energy Spectroscopic Instrument, a large survey mapping the three-dimensional positions of tens of millions of galaxies and quasars, have hinted that the strength of dark energy might not be perfectly constant over cosmic history, as the simplest version of the standard model assumes, but might instead be slowly evolving over time. While this particular finding is not directly connected to the axis of evil, it fits into the same broader pattern we have been discussing throughout tonight's exploration, a pattern in which increasingly precise measurements are gradually revealing small but persistent cracks in a cosmological model that, for decades, appeared to describe the universe almost perfectly. Some theorists have even begun exploring whether an evolving dark energy component and a genuinely anisotropic universe might be connected at some deeper theoretical level. Though this remains highly speculative territory, discussed mostly at the frontier of current research rather than in settled textbook physics. Turning back toward the specific question of the cosmic microwave background, it is worth mentioning one additional related anomaly that has drawn considerable attention over the years, sometimes discussed alongside the axis of evil, though it is technically a distinct phenomenon. This is the so-called cold spot, an unusually large region of the sky, roughly centered in the southern galactic hemisphere, that appears noticeably colder than the surrounding cosmic microwave background, more so than standard statistical fluctuations would typically predict. Various explanations have been proposed for this particular feature over the years, ranging from a genuinely enormous supervoid lying directly along our line of sight, which would cause passing light to lose a small amount of energy as it climbs out of the void's shallow gravitational well, to more exotic possibilities involving the imprint of a separate, causally disconnected universe colliding with our own during the earliest moments of cosmic inflation, an idea sometimes associated with certain variants of what is known as eternal inflation theory. While the cold spot and the axis of evil are generally treated as separate anomalies within the technical literature, both serve as useful reminders that the cosmic microwave background, despite its overall remarkable uniformity, continues to harbor unusual, statistically significant features that resist easy explanation, features that continue to motivate new generations of increasingly sensitive instruments and increasingly careful statistical analysis. Speaking of new instruments, it is worth spending a little more time describing exactly what the next generation of cosmic microwave background experiments hopes to accomplish, since much of the eventual resolution to this ongoing mystery will likely come from their data. The Simons Observatory, situated at high altitude in the Atacama Desert of northern Chile, a location chosen specifically for its extremely dry air and stable atmospheric conditions, both of which are essential for observing faint microwave signals from the ground, began collecting substantial amounts of data during the middle years of this decade, using a combination of large and small aperture telescopes equipped with tens of thousands of individual detectors. Its primary scientific goals include searching for extremely faint gravitational wave signatures imprinted on the polarization of the cosmic microwave background during the earliest moments of cosmic inflation, alongside more precise measurements of the same temperature and polarization anisotropies that originally revealed the axis of evil. The Light BRD mission, led by the Japan Aerospace Exploration Agency in collaboration with international partners, including NASA and various European research institutions, is a dedicated satellite mission, currently planned for launch later this decade, designed specifically to measure the polarization of the cosmic microwave background across the entire sky with unprecedented precision, free from the atmospheric interference that limits ground-based observatories like the Simons Observatory. Meanwhile, an even larger, more ambitious ground-based project known as CMB Stage 4 is currently in active development, planned to combine dozens of individual telescopes and hundreds of thousands of detectors spread across multiple observing sites, aiming to produce the most sensitive and comprehensive map of the cosmic microwave background ever assembled. Collectively, these new missions share a common set of scientific priorities: refining our understanding of cosmic inflation, tightening constraints on the total mass of neutrinos, searching for any hint of new, undiscovered particles that might have been present during the earliest moments of the universe, and relevant to tonight's discussion, providing dramatically improved measurements of the large-scale polarization patterns needed to finally settle whether the axis of evil represents a genuine physical feature of the vacuum or an unusually persistent statistical illusion. Given the sensitivity improvements these instruments promise, many researchers active in the field expect a considerably clearer picture to emerge sometime within the next decade. One way or the other, it is worth pausing here to consider just how unusual this entire situation is from a broader historical perspective. Modern cosmology is, in many ways, a remarkably young science. Serious quantitative study of the overall structure and history of the universe as a whole really only began in earnest during the 20th century, following Einstein's development of general relativity and Hubble's observational confirmation of cosmic expansion. Within just the span of roughly one human lifetime, our understanding has progressed from a universe assumed to be static, eternal, and essentially unchanging to a dynamic, expanding cosmos with a definite beginning, a precisely measurable age, and an increasingly detailed, though still incomplete, physical history stretching back to within a tiny fraction of a second after that beginning. Given how young this field of study still is, it should perhaps not be entirely surprising that genuine anomalies continue to surface even within our most careful, most sophisticated measurements. Every scientific field passes through periods where existing theory encounters observations it cannot fully explain, periods that often precede genuine conceptual breakthroughs, though they can equally often resolve into more mundane explanations, involving previously unrecognized sources of measurement error. What makes the axis of evil and the broader family of related anomalies we have discussed tonight particularly interesting is simply the sheer diversity of independent measurements now converging on roughly similar conclusions. It is one thing for a single satellite using a single instrument to report an unusual pattern. It is something else entirely when that same basic pattern, or something reasonably close to it, shows up independently in the motion of galaxy clusters measured through an entirely different physical effect. In the spin orientation of ancient supermassive black holes measured through yet another entirely different technique, and possibly even in subtle rotations of polarized light emitted by distant radio galaxies, using yet a fourth, entirely separate observational method. This kind of convergence across genuinely independent lines of evidence is precisely the sort of pattern that, historically, has often preceded major shifts in scientific understanding, though it remains entirely possible, and worth stating honestly, that some or even all of these independent measurements share a common, mundane source of systematic error that has simply not yet been identified. As we bring this particular exploration to a gentle close, it is worth returning one final time to the deeper philosophical question sitting quietly underneath all of this technical detail. Human beings have spent the better part of recorded history gradually coming to terms with our own apparent insignificance within the vast scale of the universe. Each new discovery, from the realization that Earth orbits the Sun rather than the reverse, to the recognition that our Sun is merely one among hundreds of billions scattered throughout our galaxy, to the eventual understanding that our galaxy itself is just one among trillions populating the observable universe, has steadily reinforced the same basic lesson. We occupy no privileged position. We are not, in any meaningful cosmic sense, special. The axis of evil and the broader constellation of anomalies surrounding it represents perhaps the first serious scientific challenge to that comfortable, long-standing narrative in quite some time. It does not claim that the universe was designed with us specifically in mind, and virtually no serious researcher working on this problem would suggest anything of the sort. But it does raise the genuinely interesting possibility that our particular vantage point within the cosmos, our specific location, our specific motion, our specific orientation in space, might be connected, in some subtle way we do not yet fully understand, to the larger scale structure and behavior of the universe as a whole. That would not necessarily mean we are special in any grand cosmic sense. It might simply mean that the relationship between an observer and the universe being observed is somewhat more intricate, somewhat more entangled than the elegant, idealized picture of a perfectly uniform cosmos has traditionally suggested. For now, that question remains open, sitting quietly at the frontier of modern cosmology, waiting patiently for more precise measurements, more careful analysis, and perhaps, eventually, an entirely new theoretical framework capable of making sense of everything we have gathered so far. Until then, we are left simply to notice the pattern, to sit with the mystery, and to keep watching that same faint, ancient light, still arriving quietly from the edge of time, still carrying with it a story we have not yet fully learned to read. It is worth taking a small detour here into a related episode from the history of cosmic microwave background research, because it illustrates so clearly just how easily galactic dust can fool even highly capable teams of scientists, and why researchers have learned to be so cautious before declaring any anomaly a genuine discovery. In March of 2014, a team of researchers working with an instrument called BICEP-2, a telescope located at the South Pole, announced what appeared to be a landmark discovery. They reported detecting a specific pattern of polarization within the cosmic microwave background, called B-mode polarization, at a level of strength that seemed to match theoretical predictions for gravitational waves generated during the earliest moments of cosmic inflation, the extraordinarily brief period of exponential expansion believed to have occurred in a tiny fraction of a second after the Big Bang. The announcement generated enormous excitement throughout the physics community and considerable attention in the wider press, since direct evidence of inflationary gravitational waves would have represented one of the most significant discoveries in the history of cosmology, providing direct observational support for a theoretical idea that, until that point, had rested largely on indirect evidence. However, within a matter of months, doubts began to emerge. Several independent researchers pointed out that the BICEP-2 team had used somewhat incomplete data regarding the amount of polarized dust emission present within our own galaxy. In the specific patch of sky their telescope had observed, dust grains within the Milky Way, aligned by the galaxy's magnetic field, produce their own faint polarized signal, one that can mimic the pattern expected from primordial gravitational waves if not properly accounted for and subtracted. When more complete dust maps, drawn from the Planck satellite's own observations, became available, they revealed that a substantial portion, and quite possibly all, of the signal originally reported by the BICEP-2 team could be explained by ordinary galactic dust, rather than by any genuine signal from the early universe. By early 2015, following a joint analysis combining data from both BICEP-2 and Planck, the original claim was effectively withdrawn, downgraded from a landmark discovery to an upper limit. A cautionary tale about the importance of thoroughly understanding foreground contamination before making bold claims about the deepest physics of the early universe. This episode is worth remembering, precisely because it demonstrates, in a very concrete and well-documented way, exactly the kind of mistake that skeptics of the axis of evil have long worried about. Galactic dust and other foreground contamination genuinely can create patterns that look, at first glance, remarkably like genuine cosmological signals. The BICEP-2 story shows that this is not merely a theoretical concern raised by overly cautious scientists, but a real trap that has caught even highly skilled, highly careful research teams working with excellent instruments. It is precisely this history that makes the eventual confirmation of the axis of evil by the Planck satellite using multiple independent frequency channels specifically designed to distinguish genuine cosmological signals from foreground contamination. So much more persuasive than the original WMAP result taken entirely on its own. Where the Bicep 2 claim collapsed once better dust maps became available, the axis of evil alignment has, so far, survived that same kind of scrutiny. It is also worth spending a bit more time on the concept of cosmic inflation itself, since it sits underneath so much of tonight's discussion, quietly shaping our expectations about what kind of universe we should expect to observe. The theory of inflation, first proposed in the early 1980s by physicists including Alan Guth, Andre Linde, and others working independently, suggests that in an extraordinarily brief interval immediately following the Big Bang, space itself expanded at an almost unimaginably rapid rate, stretching the universe by an enormous factor in a fraction of a second. This brief period of extreme expansion solves several long-standing puzzles in cosmology, including why the universe appears so remarkably flat on large scales, and why regions of the sky on opposite sides of the observable universe, regions that never could have been in direct physical contact given the finite speed of light and the age of the universe, nonetheless display such strikingly similar temperatures and properties. Inflation also provides the theoretical mechanism believed responsible for generating the tiny density fluctuations that later grew into all of the structure we observe today, including galaxies, clusters of galaxies, and the enormous cosmic web of filaments and voids stretching across the observable universe. According to standard inflationary theory, these fluctuations arose from tiny, random quantum mechanical fluctuations stretched to enormous macroscopic scales by the rapid expansion of space itself. Because these fluctuations are fundamentally quantum mechanical and random in origin, standard inflationary theory predicts that the resulting pattern of fluctuations, including the various multipoles we discussed earlier in tonight's exploration, should show no particular preferred direction, no correlation between different scales, and no connection whatsoever to the later, essentially arbitrary orientation of any particular solar system that might eventually form billions of years afterward. This is precisely why the axis of evil poses such a direct challenge to the simplest and most widely accepted version of inflationary theory. If the fluctuations really did arise from purely random quantum processes, entirely independent of one another, there is no straightforward mechanism within standard inflation that would cause the quadrupole and octupole to align with each other, let alone to align specifically with the later, essentially coincidental orientation of our own solar system. Some theorists have proposed modifications to standard inflationary theory that could, in principle, produce this kind of alignment, generally by introducing some form of anisotropy directly into the physics governing the inflationary period itself, effectively pushing the puzzle back one step further in cosmic history, from the moment the cosmic microwave background was released to the still earlier and even less well understood period of inflation itself. Other theorists prefer to look for entirely separate physical mechanisms occurring after inflation, but before the release of the cosmic microwave background, capable of imprinting this kind of alignment onto an otherwise standard isotropic inflationary background. Mechanisms such as the primordial magnetic fields we discussed earlier. It is worth mentioning, too, that inflation itself remains an area of active theoretical development, with numerous competing versions of the theory currently under investigation, differing in their detailed predictions regarding the exact statistical properties of the resulting fluctuations. Some of these variant models predict slightly different patterns of what physicists call non-Gaussianity, subtle deviations from perfectly random statistical behavior in the distribution of fluctuations. Deviations that future missions like LIGHT-BRD and CMB Stage 4 are specifically designed to help detect or rule out. If any of these variant inflationary models eventually prove more accurate than the simplest standard version, they might also help explain some of the unusual alignment patterns we have discussed throughout tonight's exploration, without requiring any of the more exotic explanations involving non-trivial topology, Finsler geometry, or holographic projection. Let us also spend a little more time considering the practical, technical side of how researchers actually search for and quantify anomalies like the axis of evil, since the statistical methods involved are themselves a genuinely fascinating part of this story. Modern cosmic microwave background analysis relies heavily on a branch of mathematics called spherical harmonic analysis, essentially an extension of the same basic mathematical tools used to describe vibrations on a drumhead or sound waves inside a musical instrument, adapted instead to describe temperature and polarization patterns spread across the surface of a sphere. In this case, the entire celestial sky as seen from Earth. Each individual multipole, whether the quadrupole, the octupole, or higher order patterns describing progressively finer scale structure, corresponds to a specific mathematical function describing a particular pattern of hot and cold regions distributed across the sky. Researchers quantify the overall alignment between different multipoles using a variety of statistical tools, including something called the multipole vector formalism, a mathematical technique that represents each individual multipole as a collection of specific directions in space, analogous to how a complicated vibration pattern can sometimes be decomposed into a handful of simpler, more fundamental component vibrations. By comparing these directional vectors across different multipoles, researchers can quantify precisely how aligned or misaligned any two particular patterns happen to be, and can calculate the statistical likelihood of observing that particular degree of alignment purely by random chance. Assuming the standard model of cosmology is correct, this kind of careful statistical analysis is precisely what allowed researchers to calculate that famous figure we mentioned earlier, the less than 0.1% probability of the observed quadrupole and octupole alignment occurring purely by chance under the standard model. It is worth emphasizing that this kind of statistical calculation, while genuinely rigorous, always depends on a variety of underlying assumptions and choices regarding exactly how the analysis is performed, which particular multipoles are compared, and how various sources of measurement uncertainty are incorporated into the final calculation. Different research teams making slightly different reasonable choices in how they conduct this analysis have sometimes arrived at somewhat different specific probability estimates, though the broad conclusion that the observed alignment is genuinely unusual and difficult to explain within the standard model has remained remarkably consistent across the vast majority of independent analyses conducted over the past 2 decades. As our exploration tonight begins to draw toward its close, it is worth reflecting one final time on what this entire episode reveals about the nature of scientific progress more broadly. Science does not typically advance through single, dramatic moments of sudden revelation. However, much popular retellings of scientific history might sometimes suggest otherwise. It advances, instead, through long, patient accumulation of careful measurement, through repeated testing and retesting of unusual results using independent instruments and independent methods, through vigorous internal debate among researchers genuinely committed to getting the answer right rather than simply confirming their own prior expectations, and through the slow, sometimes uncomfortable process of updating cherished theoretical frameworks when the evidence genuinely demands it. The axis of evil has now survived more than 2 decades of exactly this kind of careful scrutiny. It has been examined using multiple independent satellites, multiple independent frequency channels, multiple independent statistical methods, and, more recently, multiple independent types of astronomical measurement entirely separate from the cosmic microwave background itself. It has not yet been definitively explained, and it remains entirely possible that some subtle, currently unrecognized source of systematic error will eventually be identified, one that finally resolves the entire puzzle in a comfortably mundane way. But it has also not gone away, despite 2 decades of exactly the kind of careful, skeptical examination that has, historically, successfully debunked countless other apparent anomalies throughout the history of cosmology. Perhaps that, more than any specific theoretical explanation we have discussed tonight, is the genuine lesson worth carrying forward. The universe remains, even after centuries of careful scientific investigation, a place capable of surprising us, a place that continues to reward patient, careful attention with genuinely unexpected discoveries. We may not yet know whether the axis of evil represents a fundamental crack in our understanding of the cosmos, or an unusually persistent illusion born of subtle, still undetected errors. But either way, the search for that answer continues to push our instruments, our mathematics, and our imagination further than they have ever gone before, out toward the very edge of observable space and time, in pursuit of a slightly clearer picture of exactly what kind of universe we happen to call home. And on that quiet, unresolved note, we can let this particular train of thought settle, the way a room slowly settles into stillness after a long conversation, the question still gently turning somewhere in the back of the mind, unhurried, patient, content for now simply to have been asked.